All right, I have one example here today on optimizing again for composite functions. This also works with a distance a distance formula problem as we did in one of our previous examples. So first of all, we want to create a diagram for this question. We have a north-south highway, and of course I would use a ruler if I were actually doing this on a piece of paper, but unfortunately I don't have a tool that makes this nice and straight, but I will do my best here. So let's make this north. North heads up to the top and south heads down to the bottom of the page. And then it intersects an east-west highway. So east should be over here on the right and west would be over here on the left. So we have this, and they intersect at point P. So this origin, I'm going to label as point P. A car is traveling east at a constant speed of 60 kilometers per hour, and it crosses P at 1 o'clock. So that car is here at P and it's heading, I'm just going to use a different color here. It is heading in this direction towards the east at 60 kilometers per hour. At that exact same time, so at 1 o'clock, when the car is at the origin, there is a truck, and the truck is north of the intersection 5 kilometers away. Okay, so I'm going to put T for truck right here. T for truck. So initially the truck is here. Initially the car is at the origin. Now, in terms of ordered pairs, that car would be initially at 0, 0, and the truck, if it's 5 kilometers away, it's going to be at the point 0, 5, if we think of this as a Cartesian plane. Okay, 0, 5 there. So that's where we begin at. So those two vehicles are exactly 5 kilometers away from each other at that time of 1 o'clock. Now that truck is heading south at a speed of 80 kilometers per hour. Okay, so it's heading that direction at a speed of 80 kilometers per hour. Find the time when the two vehicles are closest to each other and the distance between them at that time. So right now they're 5 kilometers apart. Now if we take some the truck's going to be heading downwards. So let's say some time has passed. The truck ends up here. Car's traveling a bit slower, so it didn't get quite as far. We could calculate this length between them that I've drawn here in yellow, which is going to be based on your Pythagorean theorem. Okay, so that might be a shorter distance rather than the 5, depending on where we are at in terms of time and distances. So let's talk about this a little further now. We know that the truck is traveling at 80 kilometers per hour. So its distance from the origin, or its ordered pair that could represent it at any time t, is going to look like this. We know that the distance that something has traveled, distance is given by speed times time. Okay, so if I let my time be, or t be the time in hours, for the truck would be going 80t kilometers, where t is the time in hours. The car would be going 60t. Now, from here, that means at any time t, that new position of the truck, it's heading due south. So its x-coordinate will stay at a 0. It started by 5, but we're going to subtract 80t, where t is the time in hours. The car started at 0, 0, and its position, let me just draw this in here, its position, the y-coordinate stays the same. It started at 0. At any time t, its new position is going to be 60t, 0. Now, we can use these two ordered pairs, this one and this one, to calculate the distance between, we can use our Pythagorean theorem with this, or our distance formula, to figure out the length of that hypotenuse of our triangle there. So let's first of all put our let statement here of let t represent the time in hours since 1 o'clock. All right, so I have my let statement there. I've also written down my distance formula. I'm using the points that I have in yellow to do the distance between those those two particular points, knowing that they're changing based on time. Now we want to find the smallest, when we want to know when the vehicles are closest to each other, so we want that distance to be a minimum. We want to take this function here and minimize it. Now, before I actually do that, I'm going to explicitly solve for d. I'm going to put d is equal to the square root of this. I also am going to simplify what I have under written here. So we're going to get d will equal the square root of, and distances are just positive, 60t all squared would be 3600 t squared. And then we're going to square the first. We're going to double that product, and we're going to square the last. We'll have a minus 800t here and a plus 6400 t squared. Okay, so then that we're going to simplify further. We're going to have the square root of, that's going to equal 10,000 t squared minus 800t plus 25. Okay, and that we know we could just rewrite that as the exponent 1/2. And then we can use our chain rule on that. So this is what we want to find the minimum of. We want to minimize that distance. What is the time that will give us the minimum distance? So this is where our calculus comes in. We're going to take that and find its derivative. Set that derivative equal to 0, solve for the critical numbers. So if you want to put the video on pause and try that, you can. All right, so I'm going to do d prime at t. Use the chain rule on this. I'm going to bring that half down. We still have our 10,000 t squared minus 800 t plus 25. That exponent gets reduced by 1, so that's now a negative 1/2 times the derivative of what's inside. So that's going to be 20,000 t minus 800. All right, let's clean that up. I'm going to slide everything down to the bottom that deserves to be on the bottom or needs to be on the bottom. We're going to have our 20,000 t minus 800 left on the top, and that's going to be over the 2 and the 10,000 t squared minus 800 t plus 25 to the exponent 1/2 now that it has slid down to the bottom. All right, so for our critical numbers, we're going to set that equal to 0 and solve that for t, which means that denominator is going to multiply both sides and to eliminate it, and we're going to end up with just 0 equaling 20,000 t minus 800. So 800 is equal to the 20,000 t. Divide both sides by 20,000, and we're going to get t equals 0.04 here. Now that's in hours, because we define time to be in hours so that we could work with our kilometers per hour. We're going to change that into minutes because that, doesn't mean a whole lot of anything when we go to explain it. So let's just do 0.04 times 60, because there's 60 minutes per every hour, and that's going to give us 2.4 minutes. So after 2.4 minutes, they're going to be closest to each other, the truck and the car. And then we need to talk about a couple of things here. First of all, is this function, is d prime at t ever undefined? Okay, so if we look at what we have here, this is a parabola here. We want to look at where our denominator could possibly be equal to 0. This is a parabola. It's opening up. It's always going to, if you plot that out on Desmos, it is going to never touch that x-axis, so it's never going to be undefined. We don't have to worry about anything happening there. We should also prove that this actually is giving us a minimum. I mean, logically it should, but we should be checking to, time has to be greater than or equal to 0, so we're going to check between these values here of time, and time being greater than 0.04. And then we're going to check just to make sure that we do reach a minimum here. So you're going to check the sign of d prime at t. If you put in like 0.01, let's say, in here, you will get a negative here. If you put in 0.05, you do get a positive here. You are decreasing and then increasing. So therefore, we definitely have a min. Therefore, a min at t equals 0.04. Okay, and then from there, the last thing we want to do is actually calculate the distance between the two vehicles. So we're going to put d at 0.04. The minutes will just be for the therefore statement. We're going to put in the actual calculation using the equation for distance up here. The square root of, I got to be able to read that, 10,000. We have 0.04 squared. So I'm just putting that into my original d at t equation here. Minus 800 times 0.04 and then plus 25. Kind of running out of room there. And then you calculate that. I think you're going to get 3. A nice round 3. And then, of course, we finish that up with a therefore statement. And we can just write the two vehicles are closest together at 1:02 p.m. And in fact, if I take that with the 2.4 minutes, the 0.4 minutes, 0.4 minutes, again, there's 60 seconds. We can make that even more accurate if we wanted to. I think that turns out to be about 24 seconds. So it's 1:02:24 p.m. if we want to be a little bit more accurate there. I don't know how accurate Bob gets with its answers in the back. And at a distance of 3 kilometers apart. So they're pretty extensive questions. They're not easy at all. I'm going to give you some questions to work on, and hopefully this goes okay.